Okay. I wanted just to add a comment concerning the result of this equation. We saw that, again, V is of the order of 10 to the 5 meters per second, tau is of the order of 10 to the minus 14. So at room temperature, when T is equal to 300 K, then L is 1 nanometer, so the result is fine, let's say. What happens when we change the temperature? So when we, for instance, try to evaluate the mean free path at low temperature. Concerning V, we know, so the idea is to investigate how the value of L changes when we decrease the temperature with respect to room temperature. Let's say this calculation is not meant to be a detailed calculation. It's just to give you an idea of the order of magnitudes and on the dependence on L on T. So do not expect to obtain a number, but just a trend. The average value of the square of the velocity is proportional to T. So here we have the velocity, so we may expect that the velocity changes as proportional to the square root of the temperature. So if T is changed, then we have that L is proportional to V, and V should scale as T to the power of 1/2. And this accounts for the dependence on V, on the temperature. Then tau. We have seen that the conductivity and the relaxation time are proportional with each other. Since the conductivity is 1 divided by the resistivity and the relaxation time are inversely proportional. What do we know concerning resistivity, in particular how resistivity changes with temperature? If you make a plot, we will evaluate later this plot, but for the moment I just give you the experimental result. If you consider a pure metal, where pure metal means no defect, no defects, no distortion of the lattice, so no problems concerning the purity of the material and its lattice structure, the resistivity is nearly linear with T. So resistivity is directly proportional to the temperature. If resistivity is directly proportional to the temperature, this means that the relaxation time is inversely proportional to the temperature. So in place of T, I'd write 1 divided by T. So this leaves you with 1 divided by T to the power of 1/2. So if you send T to 0, L should in principle go to infinity. Now, that will not happen, as the actual dependence of resistivity as a function of T at low temperature is slightly different, and also some other contribution may prevent this value to go to 0. But in principle, you should have that the mean free path increases as you decrease the temperature. And this, so this is something that you do not expect, because if the scattering is between the electrons and the ions, it doesn't happen. Then when the temperature decreases, the lattice expands, or the average distance between the ion changes, because the average distance is always the same, or in general decreases, because as you reduce the temperature, you have the lattice shrinks. So you have eventually maybe a reduction of the distance, not an increase. And in general, if you have a change of the distance, that change is, let's say, very, very small. So you may expect that the distance between the ions is always the same if you change the temperature. So it appears to be quite strange, the fact that the mean free path changes that much as you change the temperature. So I add this comment not to say, okay, let's remove the Drude model because that doesn't work. The Drude model actually works in many different cases. But I wanted to point out this feature just to keep in mind that we have some problems with the scattering mechanisms. That means for what concerns Drude, the scattering was with the ions, but this conclusion that in general may be fine is not in favor of a scattering with the ions, because the ions are always there. So it's not possible that you have such a huge change of the mean free path as temperature changes. So my idea is just to put a question mark over the motivation of the collision, not on the mechanism of collisions. So the mechanism of collisions is fine. Something has to be there because otherwise we have no resistivity. So some mechanism has to be introduced in the system. Maybe the mechanism that is due to the collision between electrons and ions is not the best one. It has to be revised. So in general, the approach is the following. Please consider that we need a scattering mechanism to justify resistivity. In the Drude case, that scattering mechanism is related to the ions, but this is against a scattering mechanism that is related with the ions. So we may just keep in mind that we need that scattering mechanism, but let's put a question mark over the source of the scattering. The source of the scattering will be identified just in the second part of the classes. So for the moment, we just keep in mind the fact that we need something that collides with the electrons. We don't know what is this something, but we need that. And for the moment, just remind that maybe the ions are not the right motivation for the scattering. So that was just to point out this point. So many times we will introduce this relaxation time without saying what is the motivation. But we know that we need that mechanism to introduce resistivity and introduce the fact that we have an energy loss. Concerning the energy loss, I would like to make just a short, this is, we have nearly 20 minutes. So I just wanted to make a short example of how using the hypothesis of this model, we may obtain the same result that is obtained classically when you try to evaluate the energy loss that you have in a conductor when you have a flow of charge through the conductor, that is the Joule heating or the power dissipation along the resistance. And to make this short calculation, let's just consider what happens. I use again when I make these pictures, I use again the collision with the ion mechanism just to make the picture. So we have the electron that collides with an ion, then the output velocity is independent of the previous velocity, so just depend on the temperature. From here to here, we have the effect of the external field, and then another collision. We erase everything, and the electron starts as a new electron after the second collision. So what happens in between these two collisions? If we suppose for the moment that the time between this collision and the next collision is t, so later we will add the average, but for the moment, just suppose that the time between these two collisions is equal to t. What is the amount of energy that the electron has acquired from time t equal to 0 to time t equal to t due to the presence of the external field? Because we suppose that we have the electric field applied to the system. In this case, due to the fact that the energy of the electron is mainly kinetic, we may evaluate the differences in the kinetic energy of the electron, where initial is as soon as the electron exits the first collision, and final is just before making the second collision. So the initial is mainly the thermal one. Final is the thermal one plus the electric field contribution. So here you have 1/2 m. I write rho of E to write the contribution to the velocity due to the electric field plus the thermal one, and then I have the contribution of the thermal velocity. So in this case, I have the thermal contribution is the same. So just one comment. Some of the operations that we'll do now have in mind the fact that you at the end need to take an average. So in principle, this and this are not strictly equal. They just share the average value. But as they share the average value, I simplify those two terms. Because again, at the end, I will make an average. So when doing the average, this and this have the same average, so I may simplify that. Also here, you have the scalar product between the velocity due to the electric field and the thermal velocity. On average, the thermal velocity is equal to 0 because the directions of the thermal velocity are completely random. So also this term can be removed. So what we have here is just the contribution that is due to the electric field. And the contribution of the electric field is m times the velocity that the electron has after a time equal to t. So I have E squared, because I have the square of the electronic charge, electric field to the power of 2, T squared times to the power of 2 divided by m squared. So here I may simplify the square of the mass with the mass that I have here. So I'm left with 1/2 E squared, electronic charge squared, electric field squared, E to the power of 2 divided by m. So this is the amount of energy that the electron, this is the difference in energy between the electron in this position and the electron in this position. So this is the energy that is lost by the electron when the electron undergoes a collision, because after the collision, we have a cancellation of any external contribution. So this is the energy loss of the electron after the second collision. At this point, to introduce the, let's say, average effect, we need to take into consideration the probability to to suffer a collision by the electron. To estimate the probability of the electron to suffer a collision, we may consider the Poisson distribution, because the Poisson distribution allows us to evaluate the probability that a certain number of events may be observed when the probability to observe those events, when there is no interaction between the appearance of the different events and the number of events that we expect to have in a certain amount of time is fixed and is known. In this case, we actually do not know the number of events that will take place in a fixed amount of time, but we know the number of events we know that the average number of events that is observed in the unit time is 1 over the relaxation time. So let's say, the rate of observation of the collision events can be estimated by 1 divided by tau. So in general, let's try to write it correctly. So if Ni is the number of events, if you want to evaluate what is the probability to observe a number of events equal to Ni, and you know what is the number of events that you have in a fixed amount of time, and this can be evaluated by multiplying time t for the rate. So if this is the rate and we have a time equal to t, the number of events that we expect to observe in that amount of time is t times the rate, or t divided by the relaxation time. So if the electron survives up to t, we have to look for the probability that the electron from time t equal to 0 to time t does not suffer any collision. So first step is, what is the probability that the electron survives up to time t? Quindi, so first step is to find the probability with mu equal to r times t, so, but with nu equal to 0, so no collisions. So this is the first step of the calculation. The second step is, if the electron survives up to time t, what is the probability that from time t to time t plus dt, the electron will suffer a collision? So, find the probability when t, the amount of time, is equal to dt, to find just one collision. The first probability can be evaluated by setting nu equal to 0. So here we have 1, the denominator we have 1, we have just e to the minus rt, or e to the minus t divided by relaxation time. So this is e to the minus t divided by relaxation time. For what concerns the second, we have the second probability is equal to e to the minus dt divided by the relaxation times again dt divided by relaxation time to the power of 1 divided by 1. dt is expected to be very small, so we may expand the exponential as 1 minus dt divided by tau. So this is 1 minus dt divided by tau times dt divided by tau. Here we have dt divided by the relaxation time minus dt divided by the relaxation time to the power of 2. Since dt is expected to be very small, dt to the power of 2 is expected to be smaller and smaller. So if we stop the calculation at the first order of approximation, we may neglect the second power of dt. So at the end, the probability to suffer a collision after a short amount of time equal to dt is equal to dt divided by tau. So at this point, we may evaluate the average energy loss of the electron by considering so the average, I write energy because E is equal to the electric field. So the average energy loss due to the electron is equal to what? The value we have just evaluated and that is this one here. Then we have to sum average over all the possible values of t from 0 to infinity by taking into consideration the probability that the electron survives up to time t, that is e to the minus t divided by relaxation time, times the probability that if the electron survives up to time t, then suffers a collision after an amount of time equal to dt. And we integrate over time. So this is the, let's say, average value of the energy loss by due to just one electron. I just write, let's say, this is a constant, so we may take that out from the integral. So at the end, we have 1/2 e squared divided by m, and the integral of t squared minus t divided by relaxation time dt divided by relaxation time. And if you evaluate the integral, what you obtain is so this is the result of the integral. And when we consider infinity, the exponential brings everything to 0 when we consider the upper limit. When we consider the lower limit, the exponential is equal to 1, and just the first term survives, because here you have t that is 0, and here you have t that is 0. So the only term that survives is this one here, with another minus in front, because that is the second estremo, the lower limit of integration. So these two simplifies with 1/2. So we have e squared electric field squared divided by m. And then we have the relaxation time to the power of 3, because there is tau squared plus times relaxation time. So this is the average energy loss. And if at the end we want to obtain we want to see whether we are able to reproduce the power loss that is found macroscopically when you consider a conductor where you have a flow of current. We do not need to consider the energy, but the energy per unit time, so the power. In this case, the unit time is the average time between one collision and the next, and that is equal to the relaxation time. So the average value of the power loss by one electron is equal to E squared, electric field squared, relaxation time to the power of 3, divided by the mass and by relaxation time. So in this case, the relaxation time is the unit time. So we have the relaxation time to the power of 2. And in this case, the point is what happens when we consider not the contribution of the single electron, but we consider the contribution of the volume. So in this case, if you look here, okay, let's do the calculation for all the electrons. If we consider a number of electrons equal to n, so the density of electrons is n, the contribution given by all the electrons is, so all is equal to the density of electrons, so we have the contribution per unit volume because we multiply by a density, times E squared relaxation time, E squared divided by m. I divided things in this ways because density times E squared times relaxation time divided by m is the conductivity. So this is sigma. So this is sigma. Yeah. Allora. Infatti non mi chiedo scusa, sorry. If you look back at the calculation, when I took the constant out of the integral, there was a relaxation time in that constant because at the denominator there was relaxation time dt divided by tau. I forgot to put that relaxation time in the constant. I think I took out of the integral just 1/2 e squared divided by m. Is that correct?
Yes.
Okay, so at that point, there is another relaxation time here, since I forgot to include the relaxation time that was at the beginning in the integral. Sorry for that. So this is not, let's say, this is not tau relaxation time to the power of 3, but is relaxation time to the power of 2, because there was an additional relaxation time in the denominator. So this is the right conclusion. So at this point here, we have just one relaxation time. So this relaxation time disappears. Yeah, and now okay. So if this is the contribution of the power loss of all the electrons per unit volume, at this point we need to evaluate the power loss of all the electrons corresponding to the volume of the conductor. So if we suppose that the conductor is a wire, that the length of the wire is L, and then the surface area of the conductor is A, we may just before making the calculation, I just rewrite this term by multiplying and dividing by the conductivity. So I have sigma squared E squared divided by sigma. So I just multiply and divide by the conductivity, and I do that because sigma times E is the density current. So in place of sigma E, I write J. So here we have J squared divided by the conductivity. And this is again the power loss per unit volume. If we now multiply by the volume, so the power loss for the conductor, we have J squared divided by sigma times the area of the conductor divided by the length. Sigma is equal to 1 divided by the resistivity. So in place of sigma, I write 1 divided by rho. Now, I multiply and divide by the area. Yeah, so this is the current. Sorry, why did I wrote L denominator? I don't understand why. And this is the second Ohm law to define resistivity. So this is the, this gives you the resistance of the conductor. So this is E squared times R, the resistance of the conductor. So in this way, starting from the microscopic approach of the scattering, what you're able to find is that the power loss, considering the average power loss per electron, then considering the electronic density and the volume of the conductor, you're able to estimate that the actual power loss of a specific conductor is equal to the square of the density of the current times the resistance of the conductor. That is what you usually find when you discuss the microscopic properties of a conductor without considering the microscopic picture. So also in this case, this was a result that starting from the microscopic picture of the system was able to give you exactly the same result that you have using the microscopic approach. So also this case here was in favor of the Drude model. And I made this calculation both because we are able to predict the macroscopic result, and also because I would use in other part of the classes the definition of probability density to suffer a collision in a small amount of time equal to dt. So I will use many times the fact that the probability to suffer a collision in a very short amount of time equal to dt is equal to dt divided by the relaxation time. Okay, so I think now it's time to end. Do you have any questions?
No, thank you.
No.
Okay, so now I stop.
I have a question, please.
Yeah, please.
In the integral of the energy loss from one electron,
yeah,
I wrote the integral of from 0 to infinity of 1/2 e squared, capital E squared, t squared on m, then the exponential e to the minus t on tau, then dt on tau, and then I wrote another dt, but I'm not sure.
Yeah, I wrote that that is not correct. So just wrote dt divided by the relaxation time.
Okay.
Otherwise, you have a dt squared. Yeah, that's correct.
Okay, thank you. I'm okay.
Ok, allora, now I stop the registration.